All right, thank you. Okay, I'm going to narrow down the topic from the entire Earth to basically the dynamics of fluids flowing inside porous media. That might be in soil, in reservoirs, etc. Well, there are several fluids trying to compete for the same space. I've tried to divide it up into chapters, and the first thing is, well, flooding experiments. Describe some experiments, some typical experiments, to give you some ideas of what this is about, what kind of questions one asks. And then I'm going to go into this question of what we call steady state flow, which seems to be the simpler case compared to the other cases one is looking at, but that's the one that has been by far the least studied. And then I need to go through with you some of the numerical tools we are using in order to study this. And we, that's the group in Trondheim, with me now, and Signe Kjelstrup over in chemistry. And then how we implement the steady state on a computer. And then I'm going to go through a few of the results here. And some of this is seen experimentally, and some of these results have not been seen experimentally yet, so they should be studied as far as we are concerned. All right, so flooding experiments. I'm going straight into the lab. I'm going to the lab in Oslo of Knut Molley, who took over the experiments from Jens Feder from the 1980s. We're really back in the 1980s now. This is when they started. And this is a two-dimensional model of a porous medium. And this is the workhorse in Oslo. It consists of two plexiglass plates, rather thick. And when the system is put together, you put contact paper on both sides here. You pour glass beads, and then you flatten this out so you make a monolayer. And then you clank it together like this, clamp it, have a light box beneath, and then you inject liquid on this side and take it out on that side, and you have blocked off these sides here and on the other side. And typically what you will have is here a fluid already in the system, which in this case would be a glycerol water solution with the right mixing ratio, so that the glass beads become invisible. Same refraction index. And then you pump in, for example, air. And you do that from one side, and it comes out on the other side, and you see these kind of patterns here. And that was hot stuff in the 1980s. It's still going on, but now one is really into the details of these kind of experiments. In physics, in fluid mechanics, one is always looking for dimensionless numbers, so to really compare the size of things in an honest way. And in this case here, there are two important numbers. The first one is the capillary number, and that is the ratio between the viscous pressure drop and the capillary pressures on the pore level. So the higher the capillary number, the faster the process is going, because the viscous pressure drops, that's what you feel when you put the pressure across the system. All right, then second dimensionless number is the viscosity ratio between the two liquids. And here are three runs of the system I just showed you at different capillary numbers. And so this is high rate, intermediate rate, and low flow rate. And what you see here at the high rate, you basically you're producing a plant, sort of the branching system of a plant. And here, as you go down, it sort of grows leaves on top of these branches. And that means there are two processes here going on at the same time. And whether you are at high capillary numbers or at low capillary numbers, there will be one of the processes or the other that dominates. Down here, it is the capillary forces that dominate. So here you have capillary instabilities, and the process is called invasion percolation. Here you have viscous fingering here. And you can see here, clearly there's a length scale here that is disappearing as you go up. We get these branches. All right, but steady state flow, what is that? Well, I just described for you now to a system where we start with everything filled with one liquid, and then we pump another liquid in there, and we look at the process going from state 1 to the state 2. It's a transient. Now, inside the reservoir, just focus on some little element. Most of the time, that is going to have a rather boring life. Whatever is statistically coming into this, or bubbles or whatever, is also leaving it. It is going to be in steady state. It is not a transient. And this is the state we want to understand. So what happens after you have had this flooding, etc., and you just still keep on pumping things into the system? That's the steady state. As I said, surprisingly enough, it has almost not been studied at all. There are a number of Greek works in the 1990s by Pyatakis group, but otherwise very, very little. Now the way Molay is implementing this in his laboratory is to have again this Teleshow cell, the two-dimensional cell, the two glass plates with glass beads in between clamped together. And then here on this side you pump in liquid 1, liquid 2, liquid 1, liquid 2, liquid 1, liquid 2, and so forth. In reality, I have quite a number of them. And you just pump them in at the same rate, and they mix over here. And if you're far enough from the inlet here, you're basically in a region where you can make a little square here, take out that square, look at the statistics there, you take another square here, and square here, and you see, apart from statistical fluctuations, it's the same. What does it look like? Here. These are artificially colored clusters of different sizes. I mean, this is in a steady state, taken at one place in the system, another place in the system, and you wait, for example, and you basically see the same thing. But the system is very much alive. These things break up, and then merge and break up and so forth. They're sort of they are self-organizing. This is the steady state. And of course, this is extremely important to understand the properties of this in reservoirs, for example, where you have a mixture of oil and water. And these things are then moving. The water is pressing on the oil is pressing on the water, and they mix, break up, and so forth. So this is the aim here. All right. So you have in the flooding experiments the capillary numbers and the viscous ratios. But in addition, when dealing with steady state flow, there are some other parameters that are obvious to control, macroscopic parameters. One is the fractional flow. That means what percentage of the total flow is liquid 1. And the saturation is what percentage of the two liquids in the system is liquid 1. The pressure across the system and the total flow rate. And it turns out, and these experiments that are going on right now, that the flow state depends only on the macroscopic parameters. So you start with your system, you go in and measure local statistical properties, you change the parameters, you turn up the flow rates, everything changes, and you go back again, and you find the same statistics as you started out with. So really, the state is given by these macroscopic properties only. That's what you need to describe it. Then everything of the details follows from this. Of course, the big question is how to get from these macroscopic quantities to the microscopic statistical distributions. But anyway, we are doing numerical work in Trondheim on this. And let me spend a few minutes on describing the model we are using. And that basically is a network where, so this is a network as you know, just a square network. But you should think of it this way. So here's the porous medium. Here are the grains the porous medium consists of, if this is a sandstone. And in between, you have the pore space. And this is a link now. Here. Here's another link. Here's another link, and here's etc. This is now, of course, a very regular network. So it gives you end up with a square lattice like this. here. But as you'll see, we'll go into much more complicated things in a little while. Each of these links look like this. They have this triangular shape, and that you can understand if you just stack oranges like this and you look at the space in between them. You'll have these crevices here, like this. And here you can see a little bubble, for example, of the liquid. So that would be a bubble inside here. And then you go from these shapes here and you make a model of the forces, etc., by having surface tensions and so forth in here. I'll not go into the absolute details there because, you know, I'll spend my talk on that, and I won't. But anyway, the difficulties in this kind of mesoscopic modeling is the following. All right, so here we have the system here. Here comes one of the liquids in, here is the other liquid, and of course it spreads out into the other links like this. What happens if you have flow like this and this at the same time? Then you'll have breakup and formation of bubbles. If you really want to understand this in absolute detail, you have to use models that resolve the system on this scale here. But and that, for example, would be methods like lattice Boltzmann, etc. But the problem is that if we were to do that, we couldn't study the collected behavior of this entire network. So what we have to do is to use our heads and invent rules for what happens and make them as realistic as possible. So then we get this mesoscopic model. We can make large networks of this type. This is not the problem. Yeah, I dropped that one. But anyway, here are some Stone Age when we started with this kind of modeling. This is back in 1998, actually. Of these kind of networks at different capillary numbers and viscosity ratios. So that's the ratio of viscosity between the two liquids. And the capillary number is basically a measure of how fast it flows. And here is a less viscous liquid moving at a pretty high rate into a more viscous liquid. And you have this immediately, these typical viscous fingers. Now here we have gone 100-fold down in flow rate, and you see a very, very different pattern. This is when these leaves or these branches I showed from the experiments in the very beginning now has completely taken over. So you have that, and this is when more viscous liquid is moving into less viscous liquid. You then have basically a stable front. And of course, this is very important for us that we have all these mechanisms in the same model at the same time, just changing the parameters. So we don't have to put anything in by hand. Now, steady state flow on the computer can be done in several ways. One is to really emulate exactly the experiment by injecting different liquids. But there's a nicer method. On a computer, you have really much control. And you can simply implement your porous medium on a torus. If you have a three-dimensional porous medium, you implement it on a four-dimensional torus. And then you just set up flow on the torus like this, on the donut. And it goes round and round and round and round. And of course it settles into a steady state. And if you open up the torus like this, you get a square like this. But of course this edge here is this edge. And this edge is that edge. So I can simply now replace this one by make a copy of it here. And the same thing here. So I basically tile the space this way. So what I have is actually an infinite system, but it repeats itself on a scale of 512 bonds in this case here. This is at 50% saturation, and it looks gray because liquid is either black or white, and it ends up to be gray here. But we have now singled out the largest cluster in this system, and that looks like this. The way it has its staggered form has to do with topology of the network. I mean, how we actually implement it. So that's a detail. Forget that. But anyway, so here you can see this largest cluster, and this is moving. In a moment, it will look very differently, and so forth. Here's something you can do on a computer, which you cannot do in an experiment, and that is to look at the flow rate distribution. And here are the flow rates now in a color coded. White means slow and dark means fast. And this is on the logarithmic scale. And what you see is basically a highway network of flow rates. And then in between, you'll have much lower rates. For people who are specialists in mechanical responses of granular media, you will recognize it because it's very much like the force network as you squeeze on a granular medium, like this. But anyway, 3 dimensions. Here's a reconstructed Berea sandstone. Basically what you do is you take a little 3 millimeter by 3 millimeter by 3 millimeter cube, you slice it up and take a picture of the surface as you slice through the system, and from that you reconstruct the pore system, I mean the topology of the of the rock, and then you extract the pore network. So here you have a few 10,000 of pores, and they are then represented as links, and each one has a few numbers associated with them to give the size of these triangles compared, how narrow it is in the middle, etc. So you really have a very detailed rendering of this. And and then there's a problem. Let me go back one step. Namely, okay, so here are the outlet bonds and here's the inlet. And if you want to now implement this on a torus, you'll have a problem because this doesn't match that. So there's a little practical thing. Well, here's an example where these edges do not match. Well, here it is. You make a mirrored copy like this, you make a mirrored copy like this, make a mirrored copy like that, and then this matches this side and this matches that side. So that's what you do. Here is now the 3-dimensional reconstructed network, and this is now a mirror copy of that, and they match here, of course, and this one matches that, and we can make it into a ring. And that's what we are looking at. And if you want the full thing, we just do the same thing in all directions, and we have it complete on a 4-dimensional torus, the surface of a 4-dimensional torus. All right, so this is what the computations look like. We start with all non-wetting liquid here. Here's the wetting liquid. And then we set up a pressure difference, even though it is, these edges are matching. And you get the typical viscous fingering here. And on this side here, you have an imbibition process. And here's further on in the process. And now these are coming back here. And this is when it has reached steady state. And of course, you see nothing but the white mist here. Now, we can go in and do the cluster structure. And here is at 59% saturation of the non-wetting liquid. And you just have these little clusters like this. These are the biggest clusters. They're all really completely cut up into small pieces. But then, as you go up in saturation, 65%, it ends up like this, 67%, and here is 71%. And this is a phase transition happening at that point. At that point, there is no internal length scale on the clusters here. And it has similarities with the percolation transition, but we don't have the precision to cut it to decide whether it is percolation or not. That we cannot. We're not there. But anyway, so here's just a rendering of the largest clusters at criticality, and this is evolving all the time, changing all the time. But this is a typical picture. All right, so you look at the cluster size distribution, you get these beautiful power laws, etc., and you get exponents out here, and they are, they are what they are. One interesting thing here is that if you look at the phase transition, this is the largest cluster as a function of saturation, and it's simply just right up like this. So it's a phase transition. But that depends on how fast the thing is flowing. So it moves as you go up in capillary number. And here's the critical saturation as functional capillary number. And that's very interesting because if you have radial flow, you will pass, you'll have this critical region somewhere away from the well. I don't know if that's useful, but for us physicists, it's wonderful. All right, and then you can do all sorts of other studies of phase transitions in this system. This is what happens, for example, when you start at the given flow rate, no saturation at all, non-wetting saturation. We increase it, and then suddenly everything starts flowing. Here's a fractional flow up like this. But when going down again, you'll have all these stuck clusters, so you have hysteresis. But if you go from the other side, start with no wetting liquid and go down, there's no hysteresis anymore. So you can play these games, and you can set up the full phase diagram. I'm just showing this because, give you a flavor of this. But anyway, so this is old hat. This is what the obvious thing to do as a physicist. But let's now go further to the stuff we are into right now. Self-organization. And basically, another word for that in this context would be permeability. What's the permeability as a function of flow rate? The Darcy equation, the simple flow equations one uses, are they correct here? And my answer is going to be no. Anyway, so let's just start, and I apologize, I have to show a few equations here. Here's the flow of a single tube. So imagine now a tube that looks like this, and it just goes on and on and on and on. And here's a bubble. You have surface tension, and they will point in opposite direction, but they will not be balanced unless that bubble sits exactly at the symmetric about this constriction. And you can identify the central mass of this bubble, and that is the coordinate I call xb here, and that's basically the total pressure drop across the bubble. It drops here and goes back again here as a function where it sits. So it's just a sine function ends up. Okay. Here is what's called the Washburn equation, which is just a small generalization of the Darcy equation. So here's the pressure drop across the tube. Here is the pressure drop across the bubble because of the surface tension. Here's the permeability, and here's the flow rate. And of course, the bubble simply follows the flow rate, because what else can it do? That means that the time derivative, the velocity of the central mass of the bubble, behaves like this. And if I have many bubbles, I get something like this. But this system here is a well-known trivial system. For example, from the book by Strogatz on dynamical systems, this is the driven over damped pendulum. So you know everything about this system. This is a classical thing from dynamical systems theory. Well, you can then get the average behavior of this bubble. And it turns out that the average flow rate in this system here goes like the pressure drop of the system squared minus a threshold pressure, the square root of that, and then just some functions that to make sure that it doesn't flow if you're below a threshold and it flows if you're above a threshold. All you should look at is really the conductance, and that is a derivative of the flow rate with respect to the pressure difference. And that looks like this. So if you start here at no pressure difference across the system, no flow, and then suddenly it jumps to infinity, and then it comes with a square root singularity down like this. And it is symmetric on the other side. In other words, here is the average flow rate as a function of pressure difference. It comes in like this and puff, with infinite slope here and here. So here's the behavior actually of a single link in this system. Here is an experimental study from the lab of Molloy again, where they have measured pressure difference of the system against capillary number, namely how fast they inject. And they find that they follow a straight line on a log-log plot. And that translates into the pressure difference going like the flow rate to what they measure is an exponent of 0.54. This is experimental. Here's an experiment from last year in Bozeman University, State University of Montana, where they have done this in 3 dimensions. They have a block of porous material like this. They drill a hole in the middle and inject from the middle radially. And here is at different saturations. And basically they see again a pressure, power law behavior of the pressure with respect to the flow rate. Delta P goes like Q to the beta. But they find an exponent that varies with the saturation. So, and it's very difficult to see any systematics in this, but I'll get to that. But anyway, remember this is now in 3 dimensions. The Molloy experiments, Talakstad, they are in 2 dimensions in a different system. Now there's a more or less forgotten paper from 1987 by this gentleman sitting over there, Hansen and Stefan Roe. And that's what happens if you try to put ketchup into a porous medium. That means a ketchup is a liquid that has a yield threshold. You have to put a pressure difference shear above a certain level for it to flow. But when it flows like a Newtonian liquid. It's just like water. Anyway, so they have this wonderful little argument saying that if I now have a network of, filled with ketchup, I put a pressure across it, delta P, and some of the links will flow, some will not. If I now change the pressure difference by delta P, a number of additional links will go above their yield threshold and start to flow. And if you don't do too much, well, then you should assume, and this is a weak assumption, that the number of additional links flowing is proportional to this pressure. And the conductance of the entire network must be proportional, also in this regime here, to the number of extra links flowing, which then is proportional to the change in pressure difference. Therefore, the change in conductivity is proportional to the change in pressure. You integrate that, and you have that. Here's Q, goes like delta P minus yield threshold and effective large-scale yield threshold squared. Take the square root of that, you get a half on this side, and you have this P. This is almost the experimental equation, except there's no PC in the experiment. So you can try to do this hand-waving argument, because it's really hand-waving, right? Better. Another thing is that, remember, we are not dealing with a Bingham liquid. We are dealing with a liquid that has a divergence in the conductivity. It comes in, the Bingham liquid will look like this and then go straight like that. This comes in and goes like this. It's more or less, abrupt puff like this. Right. Okay. So you can try to put this on mathematical terms, this argument. And then you go into literature and you find a wonderful, forgotten reviews of modern physics, because it's on percolation, and percolation is basically a used up problem now, almost. There, Kirkpatrick invents an effective medium theory to calculate the conductance of a percolating system. And he derives a formula which is very general to get the effective medium. And if you stop at the calculation at that point, you get this formula here, and you have to solve it. And then you put in the percolation details, and you get percolation. But we are going to do something else. Let me tell you what this formula is. sigma is now the conductance of a bond in the network. So there's this bond here, and there's a network around it. I want to replace all the other bonds by identical bonds, but with a behavior which is such that for this bond, it won't see the difference between the real network, which is disordered, and a network with all the other bonds equal. This would be the effective medium conductivities. And that's what I'm after. And this equation here gives me that. So this is the effective medium value, the conductance of the bond I'm looking at, and then averaged. I then solve the equation, and what I find is that, and okay, I put in here, of course, the conductance that has this square root divergence. I mean, really what we found. And it turns out you can put in a square root or whatever. It doesn't matter, you get the same result. And the result is this, that effective bonds will have a conductance which is linear in excess pressure. So there's a pressure threshold. If you're below that, no flow. If you're above, well, then it's linear. Integrate, and you get exactly the behavior as a Bingham. And you can show that, Bingham, if this is the flow rate, pressure here, here's the flow rate, here's the threshold, here's the Bingham. Here would be an extreme liquid, comes in like that and goes out like that. So, like this. And then in between you have this. And you can have everything you want in between here, and you always get the same. It's basically indestructible, this two. And then you have the total flow rate, which is then just now a homogeneous network, all bonds equal. You can calculate it immediately. And you find flow rate goes like the pressure, overshoot pressure with a threshold squared. You run this on the computer, and you do this here with the toroidal boundary conditions. That means the donut boundary conditions. Low capillary number. And then it shifts and becomes linear like this. This is the Darcy regime. That's when everything is now flowing. But below that, you go into this other regime, and this is exponentially measured. And this is at different saturations and at different viscosity ratios. It is always a half, this exponent. And here is with the precise boundary conditions used in experiments. And you see, and you can also see, the number decays. If you try to do this experiment, you'll have the apparatus on the walls in pieces. We got the data from the Montana group, and we put their data in, analyzed our way, by assuming a threshold. And this is the data they have. So now we have started collaborating with them, and they're now redoing their experiments to get a much longer range here. And we'll see. The thing is, to get this wandering exponent, if you are forgetting that there should be a threshold pressure, you have to put in threshold pressure. If you know, yeah. All right. So this is just to summarize. So here's what we basically have, a new Darcy equation in the steady state regime where you have competition between the two liquids, and that's precisely the regime that's interesting, not too far away from oil wells, for example, where all the oil and the water is, not all, but they are in competition. The single links effectively behave like this. But remember that there's disorder, so these get smeared out. And the smearing out turns this behavior on the law scale into this behavior with the square. The square root turns into a 2, and that 2 is indestructible, as far as we can see. Back to the experiments. The way the system was set up there, you create basically one of the liquids are percolating. So therefore, you would expect the threshold to be 0 in experiments in Oslo. But if you look carefully, even here, it's not quite 0. It is slightly bent. So basically, we think that the correct law is this. You have to have a threshold here. Then it should work all over. Let me now turn from something which is slightly older, but we're still very much trying to understand this, and that is what happens if you have two liquids inside the porous medium. By the way, time. Excuse me. Sorry. Perfect. Yep. So you have now, here's a wetting liquid, here's wetting liquid. In between you have a non-wetting liquid. So you can imagine that this, for example, is inside a porous medium, and I have a big blob of non-wetting liquid sitting inside wetting liquid. And the wetting liquid is now flowing. What happens to the surface here? If you go in the literature, you'll see that people describe this as a Helmholtz shear type instability. This is what you see in clouds, for example. You have shear in the air here, and you have these rolls here. You have some from numerical computations of this. Does this happen in a porous medium? I mean, the porous medium itself is a big perturbation on the system. So this is how we do it. So here's the wetting liquid, non-wetting liquid, wetting liquid. And everything is now flowing. And just to make life simple, they have the same viscosity, so they flow at the same rate. Everything. And then you increase the flow rate. What happens to this here? What happens is quite interesting. And, okay, there's going to be something obvious here and a big surprise. The first thing is the obvious thing, namely that, okay, at some point, there's this white liquid is now the non-viscous, less viscous, no. This is the less wetting liquid, the more wetting liquid, and you'll have viscous fingering instability. So you have these fingers now flowing in like this. But these fingers, they do not survive because they meet the cross flow here. So they get broken up. So you get these bubbles. So what happens is that you create a foam here on this surface. I'm off the camera. So you create these bubbles here that are moving off. So the thing is flowing like this. You get bubbles of non-wetting liquid moving into the wetting liquid. They basically do move in diffusively. And in here, you'll basically have a region that's a little bit like a foam, full of little bubbles. But then you can analyze. So how does this system evolve? The way to analyze it, we thought, was this. So you make a cut through the system like this, and you count, all right, along this line here, it's all 100% wetting liquid. Up, here's non-wetting, going back to wetting. Here's up to 100% non-wetting, and so forth. You get a profile. And then you average line by line like this. This gives you a profile. And this is what this profile looks like. So, of course, in the middle, we have 100% non-wetting liquid, and it drops down like this. And this is now the bubbles coming out. That's why it's not 0. And you see it moves inwards like this with time. This because it's being eaten away. Take the derivative of that curve. So here's the derivative of the wetting profile with respect to position. And we get, of course, a bob like this, and then boom. So it's a derivative of a curve that looks like this, right? And this is at regular intervals. Now you notice here that you can rescale this. This if you change the variable here from x position to x minus a velocity times t, they all fall on top of each other like this. That is a strange result, because this foam layer here moves at a constant speed without changing shape. So it moves actually as a solitary wave. It's a solitary layer, and it's completely stable. My intuition would have been that this would have spread out and just, become like this, but it doesn't. It moves very, very well defined like this. So we have a steady state in a reference frame moving with a constant speed to the right here. And that's a completely open question. What on earth stabilizes it? And what is the range for the stabilization? I mean, the explanation I've given and the parameters used here are those that would give, if the flow had been in this direction, viscous fingers. What happens if you are dealing with stable invasion, for example? We don't know. We're just not there yet. So this is an open question. It would be very nice to see this, if this is true in the lab, and it would be at least as nice to try to understand why. Yeah. Before I end, let me just also go into the forefront where we are right now. So here's the profile of the tubes. So they're triangular like this. And we will have systems which are completely wetting, typically. In this case here, you'll have the water completely wetting, and the water will then typically sit in the crevices. So you'll have simultaneous flow of oil inside the pore like this. So the pore comes out like this. Here's the tube. This is a cross section. All right. You can set up the equations of motion for this system. And that basically is to balance forces here. That gives the thickness of this film. And you'll have bubbles also. So basically what we are doing is to have 4 scenarios. We have completely wetting filled tube. We'll have one where we have a bubble of non-wetting liquid like this with films. Here we have a through-going film, and here we have a bubble of wetting liquid with non-wetting liquids on both sides. And then we have to go back and carefully invent these rules, try to get the correct rules. And we have studied quite a bit the dynamics of these films, and they are actually quite wonderful also. They have solitary waves, and they map onto a non-linear diffusion equation with non-Einsteinian behavior, for example. There's a lot of interesting stuff here. But anyway, here's our network. Red is links filled with wetting liquid, or non-wetting liquid. Here's the wetting liquid. And basically the experiment here is to stick this into a beaker of wetting liquid and see how it races. And you find, for example, let me just go to the next slide right away, that the amount of wetting liquid in the tube goes like the square root of time, which is the Washburn law, for example. So these are classical things that has to be there for us to believe the model. And then when it's all in place, we'll use it for new studies. But that's beginning work. So let me stop right now. Thank you.